So moving right along, we'll get to LC circuits and electromagnetic oscillations. So an LC circuit has a capacitor and has an inductor in it, but nothing else. So we haven't driven this with a source of EMF. So let's say we have our capacitor charged up to some maximum value. So it's got charge on it. When we close this switch and make this connection, this charge is free to flow through our inductor and equilibrate onto the other side of our capacitor. And I guess I've drawn that the wrong way because my positive sign's on top. So let's switch the direction I've drawn that. Charge would flow in this direction, right? From the positive to the negative plate in our traditional current direction. Okay, so we've idealized this inductor to assume that it has no resistance at this point. So we have a perfect ideal inductor and a perfect capacitor. So initially, our capacitor has a voltage of Q over C across it, right? So we'll call that our initial voltage. And then it begins to discharge. So we would write our loop equation as, whoops, that should be a plus, Q over C equals 0. We would write our loop equation in that way. So remember that our EMF as we go across our inductor is going to be in the opposite direction, hence the negative sign, di dt. And as we go across here, we're going to have a plus QC. All right, so our charge leaves the positive plate to produce a current. So since our charge is leaving that positive plate, our current is, we can write as the loss of charge from that positive plate, so a negative dq dt. So our loop equation, if we substitute this information in, really becomes negative L and I is really negative dq dt. So we're taking a second derivative there. All right, so far we've got something that looks like this. And let's rewrite that in a little bit of a neater way. So I am going to rewrite that. We've got two negative signs here on our first term. So I'm going to write that as the second derivative of Q with respect to T. And I'm going to divide my L out of there. And so it hangs on to this Q over LC over here. And that's equal to 0. So it turns out that this thing right here that describes how charge is moving around in this circuit is the same form of differential equation as the simple harmonic oscillator. So I know that simple harmonic oscillators are supposed to go on the very end of physics 1, and I know often the very end of physics 1 is super duper rushed. So I don't know that you guys have this information. So our separated on this page, it'll be easier for that. The solution here is that our charge looks like this. So it's a cosine function. It's something that oscillates sinusoidally, you would say. That phi is a constant that depends on the initial conditions. So does Q0. So phi is the phase. And we can choose to call time equals 0 in a place where we can make that phi equals 0. So these depend on initial conditions, or basically when we call time equals 0. And you can double check that this is true. All you would do, so I don't expect you guys to have differential equations yet, but all you would do is take two derivatives of this and plug it in here and see if I take the second derivative of this and add it to this equation divided by L over C, do I get 0? And you will see that that is a solution that works out for Q. Okay, so I said this is a harmonic oscillator. I'll give you the solution. Same form as the simple harmonic oscillator. So what it looks like, and this is an image from your book, is at first we have all the energy stored in an electric field of this capacitor. And then as current starts to flow, we get energy transferring to the magnetic field of our inductor, back to the electric field, but in the opposite direction, back to the magnetic field, again in the opposite direction, and back and forth like that. So it's like an oscillator that is oscillating around an equilibrium, which remember, there's at one point where we're at our maximum potential energy, there's another point where we're at our maximum kinetic energy, and then back to our maximum potential, and that oscillation happens like that. So you can look at this comparison, and this is true for a lot of things in physics. As soon as we get to a differential equation where we go, aha, I've seen that before, we've already got the solution in this simple harmonic oscillator, and we can apply that to our current situation. So let's apply it to our current situation. So if we've got an LC circuit, so an inductor and capacitor circuit, in this way, we've got a differential equation that looks like this, that we know we have a solution to. We know our solution would look like this. And one of the ways to solve this differential equation is to just say we need an equation that when we take a second derivative, yeah, maybe we have some stuff in front, but we get our original equation back. That's what the cosine function does. We get a second derivative and we get this thing back. Your book, actually no, they just used omega here. So we're going to use omega as an angular frequency. And we can figure out that omega squared equals 1 over LC just from this equation here. That should be an LC right there. So omega, that's our angular frequency, tells us how quickly this function repeats. So omega is related to a linear frequency by 2 pi. So remember, frequency is usually given in hertz. Angular frequency is in radians per second. So 2 pi times f should be 1 over LC. So if you know the inductance and the capacitance of your circuit, you can figure out how quickly that circuit will oscillate. So the charge on the capacitor oscillates sinusoidally. Okay, so we can look at that. In this case, I've already given you this equation, but it's worth writing down again. So we've got a maximum. So we'll label it Q max before I labeled it Q0. And cosine omega t. In this case, in this example, our phase equals 0. So we're starting out at our maximum Q. So cosine is starting out at its maximum value because cosine of 0 equals 1. We're starting out at that maximum Q. And since we know a relationship between Q and I already, I is negative dq dt, right? Because we define current as how our charge leaves that positive capacitor plate. I equals, so we just need to take a derivative of that equation above. And again, our phi here is 0, so I'm just going to drop it from our equation. Now, this stuff in front, let's just call that our Imax. And so that's omega times Qmax, or Qmax divided by the square root of L times C. Right? And that's our maximum current that you can see right here. And since we're starting out with a sine function, you can see that in this case, your book has actually created a definition of the current with a positive sign here. So they would have a negative sign in their function in front of that omega Qmax. If we're talking about LC circuits and those oscillations, we should talk about the energy of those oscillations. So at the start of our situation, when we have all the charge on the capacitor, so we have max charge on the capacitor, we're going to see that all of our potential energy is going to be in that electric field. At any given time, we can say that the energy stored in the electric field is related to the charge on the capacitor and the capacitance of the capacitor. So if we want to write down what we have for our equation for what the charge on the capacitor is as a function of time, we're going to write down Qmax squared and the function cosine squared omega t. We'll include our phase angle this time, but in our example, that phase angle has been 0. And we'll divide by 1/2 and c, so 2c. At a later time, when we start to build up a magnetic field, any energy in the magnetic field is going to be given by a 1/2 times L, so the strength of our inductor, times I squared. So we have, again, an equation for what I should be. So we're going to write that equation in terms of omega Qmax squared, sine squared, and then our argument in the sine squared function is, again, omega t times phi, and here on the bottom, we've got a 2. Because we have the relationship that, and I'll write this in red, that omega squared equals 1 over LC, we can put that in right here, and we'll cancel out an L. So that gets our energy equation for the energy that's stored in the magnetic field at any given time to be related to Qmax squared over 2c. So that's looking like the energy in the electric field a little bit, except now we have the sine function squared with the argument in that sine function being omega t plus phi. So the energy stored in the electric field of a capacitor and then gets stored in the magnetic field of the inductor, and it oscillates like this with the sine squared or the cosine squared function. If we look at what happens when we just set phi equal to 0, and the way we do that is at time equals 0, we start all our energy in the electric field and none of our energy in the magnetic field. That just means these equations look like Qmax squared over 2c, and this is cosine squared omega t, right? So at time equals 0, this cosine function just equals 1, and we're at our Qmax squared over 2c here in our electric field. And for our magnetic field, we've got Qmax squared over 2c. So again, that's the amplitude of our function. And we've got sine squared omega t, right? So it turns out if you add up these two energies, you get the total energy. So our total energy is just going to be the addition of the energy that's stored in our electric field and the potential energy that's stored in our magnetic field. That total energy, if we look at it, both have this function or this factor of Q max squared over 2C in the front. And then we've got a cosine squared plus a sine squared. And anytime you see cosine squared plus sine squared, you should totally rejoice, because there's an identity, a trig identity, that just equals 1. So our total energy at any given time just equals our maximum charge squared over 2C. So that's our total energy. There is no time component in that, right? That's just a constant. So if our energy is constant, that means our energy is conserved. So that's kind of cool. So our energy just bounces back and forth between our magnetic field and our electric field when we have this ideal situation where we have no